All right, so announcements. We have an exam in 2 days. How is the study guide prep going?
No.
I did notice that there's no keep slides.
Oh, yeah, I didn't get the slides up. I will probably remember that. If I don't, send me an email. What else? We have a study session tomorrow, so please come with as many questions as you can off the study guide to give us some stuff to do tomorrow. What else? We have an assignment due tonight. I will get the optional assignment up either today or tomorrow. My focus today is mainly going to be on writing the exam. That needs to happen first, but as soon as that's done, I will switch focus to making some kind of extra assignment for next week. That will be some kind of optional assignment in some way, shape, or form.
For tonight's homework, we had a height and a depth method that we were writing.
Yeah,
Can you just clarify a tree with one node has a height of one?
height of 0. It's a, yeah, height of 1 and the node is at depth 0. Yeah, yeah. Yeah,
I just wasn't sure it was a height of 0 or 1.
height is the number of levels. And then the depth,
So the root is at depth 0.
yeah, root is at depth 0. Great clarification. So we're gonna move into a section on graph searching because we talked about how to represent graphs, but we have not really talked about how to work with that structure. So we have this internal structure either in an adjacency matrix or an adjacency list, and we want to be able to answer some questions about the graph. Right, I don't want to. Right, a second monitor. Okay. That works. This would be better. All right. So we will have some internal representation of a graph, either in an adjacency matrix or an adjacency list. We want to answer some kind of question about it. Some of the questions that we could answer would be the questions that I asked you about the runtimes of on the previous slides, like what are the neighbors, the out edges from this node? What are the in edges from this node? Is there an edge between these two nodes? Those kinds of questions. But there are some additional questions that we might care about for certain graphs, like how do we minimize the cost of traversing the graph from one vertex to another? So we have an initial vertex, a source vertex, and a destination vertex, and we want to get there as quickly as possible. There are two ways that we can attempt to answer that question. So we can either use the total number of edges traversed. This is most frequently done in unweighted graphs, where we just care about the number of edges. But as soon as we have weights on those edges, we want to minimize the weight of the path that we take. So here's an example. Here's a graph. What is the cheapest, since now these edges are in the amount of money that it costs to fly between these destinations? Not exactly realistic flight costs anymore, but getting from Miami to San Francisco, SFO. cheapest way to get there.
DFW to LAX to SFO.
So there to there, to there to there,
Going up and to the lot, be cheaper.
here to here to here. I think that's the right answer. So going from Miami to Dallas, Fort Worth to Chicago to San Francisco. I think that is the cheapest. So how were you processing this to try to find that answer? What processes were you using as you did this?
How about you find that and you see it? See what, depending on cost.
Yeah. As humans, we are so very good at that multi-processing where you can take a bunch of things and very quickly hone in on, well, this looks like it's going to be part of the right answer, so I'm going to, you start ignoring things out here and ignoring things out here, and you focus in on the part of the graph that is going to most likely contain the right answer. Think about how could you algorithmatize or write a program that had a similar kind of logic to human intuition. Because human intuition is very powerful, and whenever we can a program that involves that human intuition, we will find algorithms that are very efficient. But we have to make sure that it's also technically correct, such that we actually find the right answer and we're done with it. Human intuition often leads us astray and we find a close to optimal but not quite optimal solution. We can't let our program terminate with a close to optimal solution. We need some way to borrow that human intuition. We'll talk about an algorithm that will actually find the right answer to this in a bit, but I first want to bring back the searches that we talked about with trees and see how we can adapt them to graphs. So the first is the depth first search. So yeah, it's back. What was the depth first search with a tree? Someone summarize what we learned about depth first search with regards to trees. Yeah, we kind of, we start at the root, but we go left, 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 left. We kind of do an in order traversal. So we start with an in order traversal and recursively always going left, always left, always left. I don't know if we get the reference. Anyway, we end up at the kind of lower left portion of the tree. But a graph doesn't really have a left and a right. We don't know how many neighbors a particular node is going to have, and there's no root to start at. So how could we generalize this concept of a depth first search and apply it to graphs? Does anyone have any intuition about how you could generalize that concept? The key comes down to we need some kind of ordering between the nodes. We need some way of sorting the nodes such that some nodes come before other nodes. So if you look at a node's neighbors, you can determine which comes first, next, 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 last, etc. via some kind of ordering. Once we do that, then there is a leftmost node to go search. So if we were looking at airport codes, for instance, we could expand or explore nodes that come earlier in the alphabet first. So if we are at, let's go back to it. If we are at ORD in Chicago and we want to expand the neighbors of this, the first one we would go to is Dallas Fort Worth. because D comes before S, L, and P. Since it's depth first, what would the next node that we expand be? It's actually kind of boring, because it's true regardless of which one. Let's find a better one. Let's say we've gone from that's boring too. A lot of these are boring. I'll give you a better example. Let's do this example. So think about depth first search. We're going to start at the node that comes first in the alphabet. That's going to be the equivalent of our root in the tree. And then come up with the sequence of nodes that a depth first search would explore, knowing that we are going to go to nodes that come earlier in the alphabet first. But it's depth first. Go with that order. We're going to be exploring this depth first. What's the first node that we visit? We start at A. What is the first node we visit? So we need to keep track of what colors would I want to use for this? Let's use green for exploring and then red for visiting. So we go from A alphabetically, we're going to go to B. Now, since we're depth first, we don't think about that we came from A or going back to A to explore things from A. We pick a direction and we're just going to go with that direction. Depth first search feels very much like an indecisive, or I guess it's a very decisive, but not a planner, but someone who's very spontaneous. They pick a direction and they just start going in that direction. There's no real planning we're going to do. It's like, all right, we're going to break ties by I want to visit the things that are first alphabetically, but I do not want to backtrack unless I have to. So we go from A to B. B can only go to E, so we're going to go to E. Once we're at E, there's only one place we can go, which is F. Once we're at F, there's only one place we can go, which is C. We've already been to E, so there's no reason to go back. So we are going to expand C. Then we're going to backtrack. There's no new place for F to explore, so we're going to expand F. There's no place for us to explore, so we're going to backtrack, and we're going to expand E. There's no place for us to go, so we're going to backtrack, and we're going to expand B. There's no place for us to go, so we're going to go back, and we're going to expand A. Now we're going to go to D. And then we need the other color again, we need to go to D. Now we have an option, G or H. Well, G comes before H, so we're just gonna go that way. And then there's only one new place for us to go, which is H, and now we've explored everywhere. So we're going to kind of expand H and then G and then D. That's one way to do it. Now, if depth first in a graph, you don't necessarily have to do the explore followed by the expand. You can decide to expand as you get somewhere and then the next place that you go. So it's more like a node left, right. It's more like a pre-order traversal than an in-order traversal. So this would work. But you have to keep track of the nodes that are currently on the, I guess it's a stack, if you're doing this recursively, the nodes that you visited, and you need to make sure that you don't go back to somewhere that you haven't yet visited, but is still on the stack. So we do something like this. This is the path that we would use to explore a node that leads to that other node. If we're just going from A to B, we find it as soon as we get there. If we're going to C, then we're going to explore the sequence A, B, E, F, C, which is what we saw. If we're going to go to D, then we can go just straight AD. We see it there as a possible transition from A. Questions on depth first search? How that works? Exploring earlier in the alphabet first. And this is assuming that we're doing this in order, which is why we don't, like, for instance, for H, we don't explore the A, B, E, F, C first. Because we would actually be doing that if we were starting from scratch, exploring H.
It seems really inefficient.
You pick a direction. If you pick the right direction, it's extremely efficient. If you pick the wrong direction, it's really inefficient. And it's the exact same thing in a tree. If what you're looking for is at the lower right part of the tree, you're gonna explore the whole tree before you get there. And if you have a deep left subtree and a shallow right subtree, and the node that you're looking for is in that shallow right subtree, you're gonna explore that entire left deep subtree before you even consider the shallow right subtree. So it really depends on how efficient, where the node is. If it's all the way down the long left subtree, it's gonna be the first thing you go find, and it'll look really efficient. But yeah, we don't really get a guarantee, we're just ordering the nodes somewhat differently. So that it's not necessarily in level order. But the benefit that we get, just like mentioned in trees, is we get a linear amount of memory. So we can run depth first search on really large structures without significant memory requirements. So let's spend a little bit of time on this. If you'd like to work with someone, you're welcome to work with a neighbor and write some pseudocode for depth first search. So you're gonna be given some kind of initial vertex and a target vertex. And depth first search should just go look for that target vertex. So first of all, make sure that you're only looking for a path, return a path from the starting node to the target node. It does not have to be the shortest path. You can also assume that there are no edge weights, so you don't need to consider how expensive it is to get from one node to another. So you're just going to be exploring neighbor nodes in a depth first search order until you find the target node. So this is pseudocode. Don't try to open an IDE and type it out in Java. Just try to come up with the logic for a depth first search. Question I think I should ask is, do we think that this DFS method is going to be recursive? It certainly is. I don't want to spend too long on this because I think that there's a lot to explain and there's still quite a bit to cover. So I'm just going to reveal what some pseudocode for this might look like. So we're going to pass into depth first search, the initial vertex V1, the target vertex V2. And we're going to kind of, again, separate this into a public and private method. There's no privacy on either of these, but the idea is that we don't need an associated path. The person who calls depth first search doesn't need to worry about what the initial path is. So we're going to just have them call a function, and then we're going to call an overloaded function that contains a path. When we start looking for the path from V1 to V2, that path is empty. So we're going to recursively call depth first search. V1 is now no longer the initial vertex, it's the current vertex. So we're going to look for a path from the current vertex to the target vertex and the path that we've seen so far. So we're going to add to the path the current vertex. We then want to mark this vertex as we've been here. This is important because if we find a cycle in our graph, we may end up back in V1, and we want to make sure that we don't come back to V1 again. If we do that, then we're going to have an arbitrarily large, we might get stuck in a depth first search cycle, which you can imagine a graph that looks like, I don't know, we have node A, node B, node C, and node D, and we want to find a path from A to D. If we do a depth first search of this and we don't store visited, the path that we're going to take is something like A to B to C to A to B to C to A to B to C to A to B to C, and we're never going to explore D because we didn't mark A as visited. If we mark A as visited, then when we're at C and looking for unvisited neighbors, we also would have visited B at that point, we're not gonna consider this path or this path as valid paths that we can traverse to nodes. Because we're going to, when we say for each unvisited neighbor n of V1, we're going to look for just the nodes that we haven't been to. And from C, at this point, we want to explore D, not the nodes that we've already explored. So this is what getting caught in a cycle loop looks like. So if you were writing any kind of graph algorithm and find that you have an infinite loop, it's likely that you're exploring nodes that you've been to before, and you should look at the code that is actually marking nodes as visited as a potential issue. So we're gonna mark that node as visited. If the node that we have visited is the target, then we found the path, and we just want to return the path, basically. And this value is going to have an associated list of nodes that is the order that we visited nodes in order to get to the destination. If this is not true, then we're gonna go through all of the neighbors of this recursively. And we're going to call depth first search. Now, instead of on V1, n is going to become the new V1, so this ordering is going to be that same natural ordering that we talked about before. So if they're strings, then we'll do it alphabetically. If they're numbers, then we'll do it in numerical order of some kind. So then we explore a new node, and we're going to do that recursively. But note that inside of this, we're going to reach this before we come back to explore the next thing. So this is what makes it depth first. So we're going to find the first neighbor of the first node, and then the first neighbor of the second node before we consider the second neighbor of the first node. So even if you have something like, let's say we have node A, node B, node C, and node D here, the depth first search order of this is going to expand D before it expands C. Because A is going to go to B, and then we're going to be looking at the first unvisited neighbor of B before we consider the second unvisited neighbor of A, even though C comes before D. Depth first looks at what is the current node that I'm at, and then looks at all of its neighbors to say which one comes first. So you can't just take a total order of all of the nodes in this graph and assume that you're going to be visiting them in that order. So the expanded order would be A, B, D, C. Questions on this pseudocode? I guess there's one more line that we should, if we go through all of the neighbors and we haven't found this path, then we know that the current node is not in the path, so we should take the node out of the path. Questions on the pseudocode? Does that make sense? All right, just like with trees, we should take a little bit of time to talk about some observations with depth first search. So it has a lot of the same pros and cons it did in its tree form. So we know that if a path exists from the source to the destination, the source to the target, then we are guaranteed to find it. Note how easy it is to find that path. You're storing it as you go. So that once you reveal the destination, you already have a structure that has stored the path. No more work needs to be done to recreate the path. You just return the path because you stored it as you were going. One of the downsides, though, is that we find a path, not necessarily the shortest path by any metric, number of edges or edge weights. Depth first search is just looking for a way to get there. It could decide that the best way to go from Spokane to Seattle is through New York City, and that's because depth first search went east first. And it found some path through New York, and then Jacksonville, Florida, and then Dallas, Texas, and then LA, and then up to Seattle. Hey, I found a path. It's way, way longer than it needs to be. So it's just going to find a path. To give you an example, here's that same. The depth first search from A to F is not going to find the fastest path or the shortest path in terms of number of edges. Depth first search from A to F returns A, B, E, F rather than A, E, F. Does everybody see why depth first search returns the former rather than the latter? Feel free to say no. I'd be happy to go over it in more detail. Since we're expanding nodes that come first in the alphabet, and that's all we know, we're not doing anything more intelligent than that. We go from A to B first, and from B to E, and we don't check, was there a path from anywhere that I've already visited to where I currently am that has fewer edges? It would be nice if when we got to E, we could see, oh, there's a path directly from A to E. Rather than going through B, I should route myself through E directly. But depth first search does not look at that information. We will look at an algorithm momentarily, quite possibly next time. We'll see if we get there. That would consider something like that. It will be updating as we find better paths. So there are more intelligent things we can do if we care about optimizing the path cost. Last questions about depth first search? All right, let's go back to our good old friend breadth first search. So just like with depth first search, we can apply breadth first search to graphs in general, just like we could apply depth first search to graphs in general. So let's talk about what was breadth first search for trees and why was that, what were the pros and cons of breadth first search? What structure were we using for it? Yeah, they were doing it in level order, which used what data structure? A queue, yeah. So in general, what we're going to be doing is, given that we have a particular starting node, we're going to be querying everything that we could reach, all of its neighbors. What can we reach with one step down every direction? Once we explore one step down every direction, then we're going to backtrack to this node and move to the next one, and then look at everything surrounding that node. So for each path that we can get to that's not the target vertex, we're going to add it to a queue to explore. So let's look at breadth first search. We're going to explore nodes that are earlier in the alphabet first. Again, we want to find a path from A to every other node in this graph. So what does breadth first search do as it does this? Thinking about that. What is the order that we do things in? And how does it work?
We're gonna try and go through the A, B, C, and a couple of movements and things.
Yeah, so we're definitely going to start with A. And we're going to say, okay, for each neighbor of A, are you the target vertex? If you're not the target vertex, then we're going to add you to the queue. So if the goal is to map from A to every other node in this, so we say, let's say we want to get to B, C, D, E, F, G, and H. And this is gonna be the path that we take. This is the sequence of nodes that we take to get there. We're going to query, all right, what are all of the neighbors of A? A can go directly to B, so the path is just go directly to B. We can get to D, so the path is just directly to D from A. We can get to E, so the path is just directly to E from A. Great. We still have some unexplored places that we need to get to, so we're going to add B, D, and E to a queue. I'm just gonna kind of draw a queue. We're gonna put in B, D, and E in alphabetical order. So now we're going to expand B, remove it from the queue, and now we're gonna query what is all of the places that we can get to from B. We can get to E, but we already have a path to E. So we're not going to rewrite the path to E. And that's the only place we can get to from B. Since we already have it in the queue, we're not going to add it again. We're going to now remove the D and explore the D. And now we want to ask, what are all of the ways to get to that? We need to kind of store this backtrack pointer that says that we got to D from A. Because this is going to become relevant when we want to find the path to places that we can get to from D. So we query all of the neighbors of D. We can get to G and we can get to H from D. So we're going to fill out this G and H, but we want to fill it out with the path that we've taken to get there. So we're going to add G and H, and the path here is A, D, G, and D, H to get there, assuming that A is at the front of all of these. I should probably be writing in front of all of these. Great, now we're going to remove E, since we've added all of the neighbors, so we're going to expand E and say, all right, we can get places from E as well. We can get to a new node, F. So we are going to add that path as well as F to our queue. We're gonna say now we can get to F, since we explored E from A, we can say to get to F, we take the path that we've come to so far, and we explore that path to get to F. Since there's still something that is not in our queue, we're going to add, or we don't have a path for, we're going to add it, we're gonna add F to our queue, because we don't know how we're gonna end up getting to C. We don't have that information yet. So we take off G, see that, sure enough. So we came from D. There's no new place to get to. So we're going to get rid of G. For H, we can get to F, that's already in the queue. We came here from there. So now we don't care about H. And for F, we can finally get to C. There's a neighbor of F when we go explore it that we can finally get back to, we can finally reach C. So the path to C is going to be however we got to F, so we can follow these back pointers. If you just do this recursively, printing at the end, then you recurse, print, return, print. So that's how you get that AEF. So we get A, E, F, and then the neighbor C becomes the last thing that we print. So that is the path to get to C. And since there are no other nodes to visit, we don't need to worry about adding C to the queue. The other way to terminate is you do add C to the queue. You go visit it. Say that you got there from F and know that there are no new neighbors. And now since the queue is empty, you terminate. So that gives us a structure that tells us the path from A to every other vertex in the graph using the fewest number of edges. So I think this is what we get here. The blue in this is just telling us we found a path that is shorter than what depth first search found for us. So we see that by going through this process, we don't just need a source and a destination, we have to run depth first search a bunch of times. It actually is pretty easy to store as we go. And rather than just having a single source and a single destination, we can do a one-to-all search pretty efficiently. Questions on how breadth first search is carried out? So spend a few minutes, write pseudocode for BFS, given an initial vertex and target vertex. Should say BFS. At least talk it out or think it out, even if you're not writing something. How would you codify this process? Is graph BFS going to be recursive? No? I agree, it is iterative. So we're going to set the queue to be the initial node. We're gonna mark the initial node as visited. And then we check if the queue is empty. If the queue is not empty, then we're going to dequeue the first element of that. If that is the target node, then we found the path. Then we go through a for each. We're going to say for each unvisited neighbor, mark it as visited and enqueue it. And then we go explore it in the queue order. So it's very simple pseudocode, very little is actually happening here, but it will explore every node. What can we learn from breadth first search? We know that it's going to return the shortest path by the number of edges from that source to the destination. It's very important that we specify that this is by the number of edges, because you can probably imagine some kind of graph where the actual shortest path by edge weight is not the same as the shortest path by number of edges. We'll go through some examples of this. So breadth first search just returns the shortest path by number of edges. Sometimes this is exactly what you want. If it is, breadth first search is the right algorithm to use. But if you have edge weights and you want to minimize the path cost, not the number of edges, then you do not want to use breadth first search. So it's certainly harder to store the sequence of nodes that you visited, but it's not impossible. As I kind of drew out, for each node, when we go explore it, we're going to place a back pointer, noting the node that we came from when we added it to the queue. Which node were we exploring when we added this node to the queue? That's the back pointer. You can just do this by adding a preview field to a particular vertex in a BFS. And then when you visit a node, you fill the preview field. And then you can recursively call the preview field, preview field, preview field, preview field whenever you find the destination. And that will tell you the path that you took to get there. So we get a trade-off between depth first search and breadth first search, which means that there's an appropriate time to use each. Depth first search, as we talked about, uses less memory and stores the path easier. This is useful if we have large structures and we don't have enough memory to store the entire structure in memory at one time. If we're querying this structure from a database, for instance, we can't store the entire thing locally. And then breadth first search is going to find the shortest path by number of edges. So that's nice. Depends on what you need out of your searching algorithm. If you just need a path and you don't care if it's the shortest path, then use depth first search. If you have the memory and you need to find the shortest path, use breadth first search. Let's talk about how expensive these things are. And I owe this too. What are the runtimes of depth first search and breadth first search in terms of the number of vertices and the number of edges in the graph? This is funny because DFA is a deterministic finite automata, which comes from the compilers class that I also teach. I probably got so ingrained in that typing DFA so many times that I just naturally typed DFA here instead of DFS. Depth first search. What do we think? Any guesses at the runtimes? Good guesses? So both run in the number of vertices plus the number of edges. Think about why this makes sense. We're exploring each vertex at most once, and we're considering each edge at most once in the process of finding the target. A common misconception is that these run in the number of vertices times the number of edges. When would this be the case? What would need to be the case in order for the running time to be the vertices times the edges? Yeah, it'd be like for each vertex, consider each edge. Or for each edge, consider each vertex. That's not the case. When we expand a node, we add it to a list of visited nodes, we're never coming back. When we explore an edge, we're never considering that edge again when we explore the next vertex. There's no reason to backtrack to nodes we've already visited, even if we're using new edges. We're not going to go back through an existing edge that we've already explored for any reason. So the intuition for that is that we're exploring each vertex or edge at most once. So we have to explore each node and each edge at most once. Once we explore it, we never need to consider it again. So we're going to stop here for today. We will be transitioning to preparing for the exam and taking the exam. Next week, we probably have 1 or 2 class periods of talking about Dijkstra's algorithm, which is the graph search algorithm that will show up time and time again in your CS education probably. So I want to get you a jump start on intuitively understanding it, and then we will transition next week into talking about how to get an internship in this field and thinking about the kinds of problems that you might see in an interview and get some practice solving those kinds of questions on the fly. And even if you're not looking for a job in this field, it's very good practice for a lot of the material we've covered in class. So that's where we're headed. And that will finish off the class. So I will see you tomorrow for our study session. Make sure you take a look at that study guide and come up with a list of questions. In the worst case, we're gonna have as few people in class as we did today. And so we're gonna have to fill up that time period with just your questions. See you tomorrow.